Hello, I'm Jokri Adhikari, and this is the week 7 of the live session for the course Secure Computation Part 1. Now, in this course, in this week, we had seen the secure implicit protocol using cryptographically secure schemes. So basically, in the implicit protocol that we have seen till now was something like this. So we have multiple parties, and all these parties wants to compute. So they have their secret inputs, let's say S1, S2, S3, S4. And they all want to compute some function f on these inputs. Now, the assumption was that the adversary, so suppose that the adversary is controlling these two parties. Now, the assumption was the adversary is unbounded adversary. That means it has unlimited resources and an unlimited computation power, but still the view of the adversary would be completely would be uniformly random with respect to. So the view of the adversary would be uniformly random. Right. So that was the assumption for this case. But now we are assuming that our adversary is a bounded adversary. That means they have the limited resources and limited computation power. So using this assumption, can we improve our MPC protocols or not? So that is the goal for this cryptographically secure MPCs. Now, by bounded adversary, we have PPT adversaries. So PPT adversary means probabilistic polynomial time adversary. That means the adversary which can run any algorithm to compute this secret in only probabilistic polynomial. The algorithms that they would run are assumed to be probabilistic polynomial algorithms. That means we can use mathematically secure, mathematically hard problems, in-proof problems, maybe so suppose that integer factorization problem. So the integer factorization problem was something like this. If we have two prime numbers p and q, and if we give you n is equals to pq, then finding this factors p and q for considerably large number p and q, it is very hard to compute this p and q from given n. Okay, so this is hard, and this is easy, or maybe you can just say that this can be done in polynomial time. So using this problem, we can actually create a cryptographically secure MPC protocol. So the next thing was the GMW protocol. So GMW protocol is actually something like the BGW protocol. So in the BGW protocol, we had seen if multiple parties have multiple shares like S1, S2, S3, S4. So if these are the shares for multiple parties, then they can compute any function f on this 4 inputs. We have seen that the linear functions, if they use semi-secret sharing, then they can use the linear functions, computing linear functions on them. But if they want to compute any multiplication circuit like x and y, so suppose x and y are two shares, sorry, x1, x2, x3, x4. These are the shares that has been given to these 4 participants. And also y1, y2, y3, y4, are the shares for corresponding to the secret y. Now, if they want to compute z, which is xy, I mean the shares for z, which is xy, then they, so in the VGW protocol, we had seen that they use some preprocessed data, right? So in using this preprocessed data, so the preprocessed data was, what was the data? So they had these three. So somehow, without the knowledge of A or B or C, these four participants somehow compute B1, B2, B3, B4, and C1, C2, C3, C4. So these shares, they compute these shares, and that's E is equals to AB. So after they compute the shares, before evaluating this multiplicative circuit, if they have this, then they can easily compute this Z, the share for Z, Z1, Z2, Z3, Z4. Now to compute this circuit, we needed the GRR, degree reduction method. And since we are using the GRR degree reduction method, then the number of the tolerance of this, I mean the number of participants that can, I mean number of participants that can be the threshold of this scheme, that was bounded by n by 2, since we are using the GRR protocol. But if you use this cryptographically secure, if we use, so maybe we can use some cryptographically secure MPC protocol, so that we can achieve this for any t less than n. So that is our goal in this so this is our goal, t less than n. So before we do this, I mean before we actually compute such share for this parties P1 to Pn, we have first seen what is oblivious transfer. So what was oblivious transfer? So oblivious transfer was something like a black box. So suppose this is our OT black box. So if at one side there is Alice, and the other side we have Bob. So both Alice and Bob, they have secret inputs M0, M1, and Bob has an input B. So these are secrets. Okay. Bob has the input B. Now, after these inputs have been given, so in this using this OT oblivious transfer protocol, so the oblivious transfer somehow lets Bob know what is the value of MB, but Bob cannot get the value of this. This is not possible to. It is not possible for Bob to get any information about M1 minus B, but Bob will get the value of MB. So that was oblivious transfer. I mean the formal definition of oblivious transfer. But how do we achieve this OT black box? That means how can we actually achieve a scheme that can actually do this? That doesn't reveal any information about M0 or M1 to Bob, or that does not reveal any information about B to Alice. So that was our, so that is our goal in this next lecture. So in this next lecture, we have seen what was RSA assumption and what was RSA hardcode predicate. So what was hardcode predicate? So hardcode predicate is basically something like this. So suppose that we have a one-way function. So what is a one-way function? So suppose we have a domain set X and a codomain set Y. And there is a function from X to Y such that X maps to Y. That is X is equals to, sorry, f of X is equals to Y. Okay, so let's just call it f of X. So this is this is what we are given. So f is a publicly known function, but x is unknown. The input is unknown. So if we are given fx, then the challenge is to compute this x. This is our challenge. Now, with the one-way function, you cannot do this. This is rather than saying that this is you cannot do this, it is much more accurate to say that it is with negligible probability an adversary can compute x given fx. So that is what the one-way function is. Right? So this is our one-way function is, but now the thing is that instead of a one-way function, we have hardcode predicate. So what is a hardcode predicate? So a hardcode predicate says that instead of finding the whole x, so there is a publicly known function, let's say h of x. So all you need to do, so suppose this is our set, let's say z, and there is a function h that maps this hx to, sorry, that maps x to hx. So now the problem is that instead of finding this, all we need to do is to find a way to, given fx, we have to find hx. So instead of x, we just have to find this hx. So the thing is, so this h, this h function is called a hardcode function or a hardcode predicate. If we can say that with negligible probability, an adversary can compute h of x given x, then we call this h as the hardcode predicate. For the function if. Okay. And using the RSA hardcode predicate. So what is this RSA hardcode predicate? We will see later. And we have also seen this in the lectures. So using this RSA hardcode predicate, we have to find. So we have seen how to construct a RSA OT based on RSA assumption. That means a oblivious transfer, a bit oblivious transfer basically. So over here we have this Alice and Bob, and this was the RSA OT, RSA based OT basically. So Alice had 2 bits, M0 and M1. Those are basically those M0, M1, B, and Bob has this input B. All belongs to 0, 1. That means this is basically 1 bit. Then Bob can find MB but not M1 minus B. So based on RSA, we have seen how to construct this RSA based OT. Okay. So now let's look at the problems that we had for week 6. Okay. So in the week 6, the first problem was something like this. So we have 6 parties, P1 to P6, and they want to perform a secure multi-NPC. And with the adversary structure under this, under which they want to achieve this, is given like this. So now we have to find out the truth, find out which one of these is the true statement or not. Okay. So the first statement is that this gamma, this adversarial structure, satisfies the Q4 condition. Okay, so just we have to find out if this given set satisfies the QK condition or not, where K can be 3, 4, 2, 3, 4, or 2. And the last, the option D says that perfectly secure MPC is possible for adversary structure this. Okay. So first, let's recall what was QK condition. Okay, sorry. So what was the QK condition? So suppose that we are given an adversary structure. It's a gamma. This is an adversary structure. This adversary structure satisfies the QK condition if the following, if we can say that there exists, oh, sorry, not there exists, but rather we can just say for all Q1, Q, okay, not Q1, Q2. Let's say for all G1, G2, GL, not GL, but GK in gamma, G1, okay, there's union of all GIs where I is 1 to K. This is a proper subset of the participants. P is basically the set of all participants. Okay, so G's are and this GIs, this G1, G2 up to GK, these are basically some randomly sampled sets from gamma. Okay, so if we take any case, any set, any k many subsets of gamma, then the union of those k many subsets must be a proper subset of P. If this is true for all of these k sets, k many sets of gamma, then we can say that this adversary structure gamma satisfies the QK condition. But if there exist such k many subsets such that this union is actually equal to P, then we can say that it doesn't satisfy QK condition. Now, in the question, we have to check whether this gamma, this given gamma, this satisfies the Q2, Q4 condition or not. So let's write down the gamma here. So gamma over here is P1, P2, P3, P1, P2, P3, P3, P4, P2, P3, P6. P1, P2, P5. So this is our gamma. Now first we have to check whether it satisfies the Q5 condition or not. Sorry, Q4 condition. So for Q4 condition, what we have here is that only 4 subsets are there, right? And if we take the union of these 4 subsets, what we get? We get P1, P2, P3 from the first subset, P4 from the second subset, P6 and P5 from the third and fourth. So this is equal to P. So that means it definitely does not satisfy the Q4 condition. Yeah, so it definitely doesn't satisfy the Q4 condition. Now let's see about the Q3 condition. So for Q3, what you have to say is that any three subset, if we take any three subset from this gamma, then that should not be the whole P. So let's see if that's true or not. Now take this three subset, 1, 2, 3. So P1, P2, P3 from these three subsets, P3, P4, oh sorry, not P3, P4. So we have P1, P2, P3, P6, P5, but P4 is not in this set. Now, for this set, we cannot really say whether the Q4, Q3 condition is satisfies or not. So now let's take this set. Okay, so over here, for these three sets, we have P1, P2, P5 from this set, then P3, P6 from this set, and finally we have P4. So this is our set of all participants P. So that means there exist three sets in this gamma such that the union of these three sets can be the whole P. Therefore, we can again say that gamma does not satisfy Q3 condition. Now what about the third one? So now instead of okay, so now instead of this gamma over here, we now have one extra set in this gamma. So now our gamma is okay. So let's there is our gamma. Okay, so now we have that there exists another set, extra set in the gamma. So that is P4, P3, P2, P4, P5. P2, P4, P5. So this is an extra set that is included in gamma. So now the question is whether this satisfies the Q2 condition or not. Okay, so there are, how many sets are there? 1, 2, 3, 4, 5, 5 sets. So now let's try to find out if there exists any set, if any pair, there exists a pair of set that covers the whole set of participants. So first, if we take these two sets, then we can say that P5 and P6 are not in the set. Right? Similarly, if we take these two sets, then P4 is not in the set. Now let's take these two sets. Now for these two sets, P1, P2, P3. So P4 is not in the set. P6 is also not in the set. Great. For these two sets, P1, P2, P3, P4, P5, but P6 is missing from this union. Great. Now let's take these sets. Now for these two sets, P1 is missing. P1, P2, P3, P4, P5 is also missing. So now just these two sets. Now for these two sets, we have missing P6. Now if we take these two, then we have only P1 missing. So anyway, you get the point. So basically what we have here is that if we take any two sets in this gamma, then you can verify that if you take the, all 10 possible pairs of these sets, then you just take union of these two sets. This will always be a proper subset. So the union will always be a proper subset of, always a proper subset of P. So this satisfies the Q2 condition. And finally, we have that D. We have D where it is said that this MPC is a perfectly secure MPC for the adversary structure this. So now we have been given the gamma as, okay, so whatever the gamma was, that union with P1, P4, P6 and P4, P6 and P4, P5. Now, how can we say that corresponding to this adversary structure, we can have a perfectly secure MPC? So, to achieve a perfectly secure MPC, this adversary structure must satisfy, gamma must satisfy the Q2 condition. So all we need to check whether this gamma satisfies Q2 condition or not. So right now, so initially gamma had four sets, and now we add this two, we have total six sets inside gamma. So the number of possible pairs would be 62, which is nothing but so basically you have to just check all these 62 many pairs in this pairs of sets in this in gamma, and if any of the pair is the union of any pair covers the whole participant set, then we can say that it does not satisfy the Q2 condition, and this is not a perfectly secure. This we cannot have a perfectly secure MPC. But in this case, we can actually, if you try to check all of these possible subsets, then you can see that this actually satisfies the Q2 condition. That means we can create a perfectly secure MPC. Okay, so let's go to the problem 2. The following statement is true for a non-threshold adversary. Okay, so in the problem 2, we have to justify the statements, or we have to say whether these statements are true or not. So the first statement is that MPC against non-threshold adversary provides better fault tolerance than the threshold adversaries or not. The second is that an MPC in the non-threshold adversary lacks flexibility, as one cannot consider the mutual relationship amongst the parties. And then the perfectly secure MPC protocols against non-threshold adversaries may work even in the cases of no corruption, number of corrupted party. Okay, sorry. So there is a mistake. So there should be the number of corrupted party is greater than the number of honest parties. So greater equals to. And finally, we have a perfectly secure MPC scheme against the non-threshold adversary with the corruption threshold T will continue to be secure against any non-threshold adversary having adversary structure gamma as long as gamma is less equals to T. So these are the 4 statements that we have. Now in the threshold model, what we had seen is that that T is always less than n by 2. If this is true, that means the number of corrupted parties T, if this is less than n by 2, then only we can have a perfectly secure So this was a necessary condition for perfectly secure MPC. But on the other hand, in the non-threshold model, what we have here is that the adversary structure gamma, let's say this is the adversary structure. So gamma must satisfy the Q2 condition. So now consider 4 parties: P1, P2, P3, P4. Now we have an adversary structure like this: P1, P2, P3, P2, P1. So this is just our adversary structure. Okay. P1, P3, and P2, P1. So this is our adversary structure. So if this is our adversary structure, then you can see that if we take these two sets and union, the union of them does not cover the P, right? So for this gamma, and for this adversary structure, we can have a actually have a secure MPC, perfectly secure MPC. But similarly, if in the threshold, if we consider the threshold model, the T must be less than 4 by 2. That means that T must be less than 2. So T, there is only one possible answer for T. That is either this is sorry, there are 2 possible answers for T. T can be either 0 or T can be 1. In the threshold model, we can actually see that for this example, for this set of parties, the number of adversaries that the threshold model can tolerate can be either no adversaries at all, which is the ideal case, or there is at most one adversary in this scheme. Then we can create a perfectly secure MPC. But in the non-threshold model, as we can see, there can be 2 adversaries. Sorry, there can be the adversary can control up to 2 parties. So threshold model is basically a general. The non-threshold model is a generalization of the threshold model. So the first is true. The first statement is true. That means that in the non-threshold adversary provides better fault tolerance than the MPC against threshold adversaries. The second one is that the MPC against non-threshold adversary lacks flexibility, as one cannot consider the mutual relationships amongst the parties. Well, one cannot consider the mutual relationships amongst the parties. Well, this is not also true. I mean, given the adversary structure, we can actually create. I mean, the adversary structure is the one that defines the mutual relationship among the parties. So, if we, I mean, for the threshold adversaries cases, the adversary structure should be all those cases, right? Sorry, if the threshold is T, then the adversary structure for that particular model should be all those sets with T participants. So this will be our adversary structure. Now, for this adversary structure, we can use the non-threshold model for this adversary structure, and we can create the MPC protocol for that. So this is not true. For C, we have this. For non-threshold case, we can even consider the case for number of corrupt parties is greater than the number of honest parties. So that is also true, because in the threshold model, to create a perfectly secure MPC, we had this. That means T is less than or equals to n by 2, which means that the number of honest parties is greater than the number of corrupt parties. So that means this was an honest majority case. The number of honest parties should be always greater than the number of corrupted parties. But in this particular example, as you can see, that if the adversary is like this, I mean, if we consider this P1, P2 to be the corrupted parties, then P1 and P3 is the corrupt parties, then P2, P4 would be the honest parties. Therefore, the number of corrupted parties is equals to the number of honest parties in this case. So we can have such cases for non-threshold model. So this is also true. And finally, what we have here is that a perfectly secure MPC scheme against a threshold adversary with a corruption T will continue to be secure against a non-threshold adversary having the adversary structure gamma as long as gamma is less equals to T. Wait a minute. MPC against a threshold adversary with a corruption threshold T will continue to be secure against a non-threshold adversary having the adversary structure as long as gamma is less equals to T. Okay. So this is actually not true. So if I mean, we could say that it was true if the condition was like this. Instead of gamma less than equals to T, we had that for all G in gamma, the cardinality of G is less than equal to T. Then we could say that, okay, this is true, because it says that it can tolerate, I mean, we have a secure MPC protocol for threshold model in the threshold model with threshold T. That means if any T many participants are corrupted, T many or less than T many participants are corrupted, then the MPC protocol is secure. So if this is true, that means for any G in the adversary structure, if the G is basically the maximal corrupted parties, right? So basically, if the G in gamma, if that is less equals to the cardinality of G is less than equals to 2, then you can say that at most T many parties can get corrupted in this adversary structure. So therefore, for that case, we can say that, okay, this is true, if this was true. But the condition says that the cardinality of gamma is less than equals to T. That means the number of sets in gamma is less equals to T. But the number of sets in gamma, it is possible that one of the sets in the gamma G has the cardinality greater than T. That is possible. So T is actually not true. And if this is actually true, the cardinality of G, one of the G is greater than T, then for this perfectly secure, sorry, for this threshold adversary with corruption threshold T, for this in the threshold model, that implicit protocol will not be secure anymore. So therefore D is not true. Okay. So let's come to problem 3. In problem 3, what we have here is that there are 4 parties, P1, P2, P3, P4. 4 parties, and the adversary structure is defined as this. Now, considering the Ito-Saito Nishizaki scheme, suppose that these 3 shares, S1, S2, and S3 have been distributed among the parties. So we have to match these shares. So let's recap on the Ito-Saito network. I mean, Ito-Saito Nishizaki scheme. So what was the scheme? So first, we have, suppose, participants P1 to Pn. Okay. Consider this P, which is P1, P2 to Pn. So this is our set of participants. And suppose we have gamma like this, G1, G2 to Gn. So L is basically some number, the number of sets in gamma. Okay. So in this scheme, first we write down all the sets in the adversary structure, and we take the complement of those sets. So there are L many sets over here. There is a dealer who have the secret S. Dealer basically creates a use the additive secret sharing scheme and creates L random shares that sums up to S. And these shares are then sent to all the participants in this set. So S1 is basically sent to this G1 complement, that is P minus G1. S2 is sent to G2 complement, and similarly SL is sent to GL complement. So all these shares are shared among this set, these parties. So now in the example that we have given, we have parties. The set of party P is given by P1, P2, P3, P4. Gamma is given by P1, P3, P1, P2, and P4. P1, P3, P1, P2, and P4. So this is our gamma. So first we write down all these sets in the gamma. Then we find the complement of the sets. So the complements over here is P2, P4, not P2, P3, P4, and P1, P2, P3. And the dealer in this side have the secret S, and corresponding to that secret, it creates three shares S1, S2, S3, such that the sum is equals to S. These three shares are supposed to be shared among these parties S1, S2, S3. So what P1 gets, what P2 gets, and what P3 gets. So the party P1 gets the shares. So there is P1 over here, and P1 is nowhere. So P1 only gets S3. What about P2? So P2 is here and here. So P2 gets S1 and S3. S1 and S3. P3 is here and here. So P3 would get S2 and S3. And finally P4 would get S1 and S2. So these are the shares that P1, P2, and P3 and P4 these participants get. So let's check the table. So P1 gets S3. So P1 should get only S3. So one should be matched with B. P2 should get S1 and S3. P2 should get S1 and S3. So 2 is matched with C. P3 should get S2 and S3. P3 gets S2 and S3. And finally, P4 gets S1 and S2. So this is our answer: 1B, 2C, 3A, 4D. So option C is our correct answer. So now we move to problem 4. So problem 4. In problem 4, we have three participants, P1, P2, and P3, and each of these participants have the inputs x1, x2, x3. Now suppose the parties are using three-party RSS protocol. The RSS means the repetitive sharing scheme. So using that protocol, this party is want to compute the function fx, and fx is defined as this. So suppose the parties carry out this efficient sharing using pre-processing phase, then which of the following statements are true? So before looking at the statements, let's look at how this RSS protocol, how does this RSS protocol works. Okay. So what was the RSS protocol? So basically, we had one secret S, and using the additive secret sharing, we create three shares of this S1, S2, S3, such that the sum is basically S. Now there are three participants. So we call these participants as P1, P2, P3. So this is a three-party protocol. So P1, P2, P3. So P1 would only get hold of S1, S2. P2 would get hold of S2, S3, and P3 would get hold of S3, S1. So somehow they would share this shares among themselves, and the reconstruction phase ensures that each party would send only one ring element. So like P1 would send S2 to P3, P3 would send S1 to P2, and P2 would send S3 to P1. And in this way, each party, so look at this, that each of the party only lacks only one share of this three shares. So, and the next party always holds, like P2 gets, P2 lacks S3, that P1 lacks S3, that is available to P2, and similarly P2 lacks S1, that is available with P3, and P3 lacks S2, that is available with P1. So if in the in the reconstruction phase, if P1 sends S2 to P3, P3 sends S1 to P2, and P2 sends S3 to P1, then each of them can reconstruct this S. So this was the reconstruction phase of RSS protocol. So the first thing that we have to take care of is how can these three parties, P1, P2, and P3, have these two shares. So suppose P1 is the one who have S. P1 is the dealer for now. So P1 has S. Now somehow P1 has P1 so basically they wants to P1 wants to generate this S1, S2, and S3 such that P1 holds S1, S2, P2 would hold S2, S3, P3 would hold S1, S1, S3, or rather I should just write S3, S1, S3, S1. So this is what P1 wants to ensure. Now, since P1 already holds the S, so it doesn't matter what share does P1 hold. So P1 wants to ensure that P2 and P3 holds this. So how can the P1 ensure that? So one way is to do it is that P1 generates this S1, S2, and S3. It keeps S1, S2 to himself and sends the S2, S3 to P2 and S3, S1 to P3. So this is the sharing stage. Now this takes one round of communication with 4 ring elements. As you can see that 2 ring elements is sent to P2 and 2 ring elements is sent to P3, and both can be sent parallelly. So there is only one round of communication with 4 ring elements are supposed to be sent to P2 and P3. But as we have seen over here that these parties carry out efficient sharing using pre-processing phase. So even though this is valid, but we need to I mean these parties use some pre-processing for the sharing and the evaluation phase. So how the pre-processing is done? So in the pre-processing phase, the idea is that P1, P2, and P3, they would hold some alpha 1, alpha 2, alpha 3, such that this alpha 1, alpha 2, alpha 3 would sum up to 0. This is the goal. So how can they do it? So P1, P2, P3, they basically select 3 random elements, beta 1, beta 2, beta 3. Then P1 sends beta 1 to P3, beta 2, sorry, P3 sends beta 3 to P2, and P2 sends beta 2 to P1. And now they can compute this alpha 1, alpha 2, alpha 3 in this way. And as you can see, the sum of alpha 1, alpha 2, alpha 3 is 0. So this is the way they can actually use the pre-processing to achieve this, to generate alpha, to share alpha 1, alpha 2, alpha 3 such that the sum is 0. So it requires one round of communication. Why? Because each of this beta 1, beta 2, beta 3 can be sent to the next participant parallelly. So it only requires one round of communication, and the total number of ring elements that is sent is 3. So this is the pre-processing. This is how the pre-processing is done. Now we need the sharing stage. So after pre-processing, how the sharing is done. So there are again 3 participants, P2, P1, P2, P3. Now suppose P1 is our dealer who holds the secret S, and they also have the pre-processed data alpha 1, alpha 2, alpha 3. So what P1 would do, P1 would so now S can be written as S plus alpha 1 plus alpha 2 plus alpha 3. Since this sum is equals to 0, so we can write it like this. So now what P1 would do is that P1 would send S plus alpha 1 to P2, P3 would send alpha 3 to P2, and P2 would send alpha 2 to P1. Now what P1 would hold is S plus alpha 1, comma alpha 2. P3 would hold S plus alpha 1, comma alpha 3. And P2 would hold alpha 3, alpha 2. So the only piece that P2 is missing is this. The only piece that P3 is missing is alpha 2. And similarly, only piece that P1 is missing is alpha 3. So this is exactly same as we had seen over here. So using this, using the preprocessed data, they can actually P1, P2, and P3 can hold an RSS sharing of S, and this only requires this sharing protocol. It requires one round of communication, and 3 ring elements are communicated, because all these 3 elements can be passed to the next person parallelly. Okay, so this is the sharing stage. So now evaluation. Now suppose that for S we have S1, S2, S2, S3, and S3, S1 as the share for S3 participants P1, P2, P3, and these are the shares that they hold. And there is another, okay, so instead of S1, S2, so suppose these are the participants P1, P2, P3, and for X they have X1, X2, X2, X3, x3, x1. These are the shares that has been shared with p1, p2, and p3. And similarly for y, we have we have y1, y2, y2, y3, and y3, y4. Now, if we want to find the share for cx plus c dy, where c, d are basically some scalar values. So basically, this is a linear combination of x and y. Then all we can do is calculate this: cx1 plus cy1, cx2 plus cy2, sorry, dy1, dy2, cx2 plus dy2, cx3 plus dy3, cx3 plus dy3, cx4 plus dy4. Sorry, should be y1. So for any linear function, we can we don't need any introduction, but rather we can just locally compute, each participants can locally compute the shares. So there is no problem with the linear functions. But what if we want to find for the multiplications xy? So how can we compute the shares with the multiplication? So xy can be written as like this: x1, x2, x3, y1, y2, y3. So this is nothing but x1, y1 plus x1, y2, x1, y3, x2, y1, x2, y2, x2, y3, x3, y1, x3, y3. So xy can be written as this. So now let's go back to the participants. So the participants P1, it has these two values. Participant P2 has these two values, these shares, and participant P3 has these shares. So what they can do is that they can generate this one. Right, so they can just generate z1 as x1 y1 plus x1 y2 plus x2 y1, z2 as x2 y2, x2 y3, y2 x3, and z3 x3 y3, x3 y1, x1 y3. Okay. So they can locally compute this z1, z2, and z3. So after they locally compute this z1, z2, z3, what these participants can do is p1, p2, p3. Okay, so one thing that we can see is if we sum up this z1, z2, and z3, then it will sum up to xy. Okay, so let's just forget about this, and we have that xy is equals to z1, z2, z3. So now p1 has z1, p2 has z2, p3 has z3. So what they can do is that p1 can just send z1 plus alpha 1 to p3, given that they have some alpha 1, alpha 2, and alpha 3, this pre-processed data with them. Z3 plus alpha 3, and it can send Z2 plus alpha 2. Then if we sum up this so if we do this, then P1 would hold Z1 and Z2 plus alpha 2. P2 would hold Z2 and Z3 plus alpha 3. P3 would hold, oh sorry, P1 would hold Z1 plus alpha 1 and this. Z2 would hold, P2 would hold Z2 plus alpha 2 and this. P3 would hold Z3 plus alpha 3 and Z1 plus alpha 1. As you can see, if we add Z3 plus alpha 3 to this, then alpha 1 plus alpha 2 plus alpha 3, that would be sum up to 0, because the preprocessed data is always sum up to 0, this alpha 1, alpha 2, alpha 3. And Z1 and the sum of Z1, Z2, Z3, that is equals to X1. So in this way, this is the evaluation phase. In this evaluation phase, what we needed was that we locally compute this Z1, Z2, Z3, each participant would do that, and then they would do a one round of communication with 3 ring elements. And they can compute this multiplication circuit. And for each multiplication circuits, we need an extra one round of communication and with 3 ring elements. And the preprocessed data for each multiplication would be different. And for each sharing, to share this data for each participants, the preprocessed data also should be randomly picked. So now let's go back to the question. So in the question, we have P1, P2, P3, and they have P1, P2, P3, and they have their secrets X1, X2, and X3, right? And they want to compute the function, sorry, not fx. So the function that it wants to compute is f of x1, x2, x3, which is x1 plus x2, x3, x1, x2, x3. X1, x3. So this is the function that is want to compute. Now, if P1 wants to share this x1 and P2 wants to share this x2 to everyone, and similarly P3 wants to share this x3 to everyone, then what P1, so for sharing each of these values, we need 3 pre-processing. And again, to compute this circuit, we need x2, x3 that are to be multiplied together. Then x1, x3 that are also to be multiplied together. This is added, and finally this value is added, and we get the final value over here. So this is the circuit that we want to evaluate, and we have 2 multiplication circuits. So for these 2 multiplication circuits, we need 2 pre-processing data. So total 5 pre-processings are required before we start sharing the values and start evaluating. So option A, it says that we will need 5 independent random 1-3 additive sharings of 0. So that means we need 5 independent random pre-processed data. So A is true. Now, Option B says that including the preprocessing and reconstruction phase, the protocol concludes in 8 rounds. So we'll check that whether it's true or not. And then the number of ring elements computed during the gate evaluation phase will be 6. We will also check that. So we will check B and C. Option D is obviously not correct because A is already correct, as we have seen. Okay. So over here, for the preprocessing, so after the preprocessing data have been generated, so X1 is shared among all these 3 parties. So that takes 1 round with 3 ring elements. Similarly, P2 would share this X2 to each of these participants. Now, the sharing of P1 and the sharing of P2 and the sharing of P3, all this sharing can be done in parallel because X1 is independent of X2 and that is also independent of X3. Right. So therefore, all this sharing can be done with 1 round, but the number of ring elements should be 3 multiplied by 3. That is total 9 ring elements in the sharing stage. Now let's come to the evaluation phase. So in the evaluation phase, P1, P2, P3, they all have their sharings. They all have their shares. Now to compute this multiplication circuit, it needs, so as we have seen, the multiplication, computing any multiplication circuit, it needs 1 round of communication with three ring elements are to be communicated in that round. So it needs 1 round of communication for this. And similarly, to compute this, it also needs 1 round of communication with 3 ring element. This is 1 round, 3 ring element. And this also takes 1 round with 3 ring elements. Now, the multiplication result of this doesn't depend on the multiplication result of x1 and x3. So therefore, these 2 multiplications, the sharing or the evaluation of these 2 multiplications can be done in parallel. So total in these 2 multiplications takes 1 round, the multiplication, the evaluation phase. In the evaluation phase, it takes 1 round of communication with 6 ring elements. Why 1 round? Because these 2 multiplications can be done in parallel. So option C, it says the number of ring elements communicated during the gate evaluation phase will be 6. So that is also true. Because no other ring elements are to be communicated after this multiplication is done. Because rest of the evaluation are only additions that can be done locally by each of the participants. Now we check this option B, that the including pre-processing and reconstruction phase, the protocol will conclude in 8 rounds. So as we have seen in the sharing can be done in 1 round. The pre-processing can be done also in 1 round. In the pre-processing, even though there are 5 pre-processing, since all this pre-processing data that was generated in this 5 pre-processing, all this data that has been generated for this 5 pre-processing are independent of each other. So all this data can be transferred, can be communicated among these parties with only 1 round. So pre-processing takes 1 round. Then comes sharing. The sharing also takes 1 round. And how many ring elements are there? For the pre-processing, since there are 5 pre-processing, and for each pre-processing, as we have seen over here, for each pre-processing, 3 ring elements are to be communicated. So there are total 15 ring elements communicated for pre-processing. For sharing, there are 9 ring elements that are communicated. Now for evaluation. For evaluation, as we have seen over here, one round is enough. But 6 ring elements are communicated in the evaluation phase. And finally, we have reconstruction. So how the reconstruction works? So reconstruction is pretty easy, because if P1 has S1, S2, P2 has S2, S3, and P3 has S3, S1, then in the reconstruction phase, P1, P2, P3 just communicates S2, S1, S3. Sorry, S2, not S2. This has to be S3. So this has to be S3. P1 sends S2 to P3, and S1 is sent to P2. So in the reconstruction phase, we only need one round of communication with 3 ring elements. So that's why in the reconstruction phase, we need only one round of communication with 3 ring elements. And this is independent of evaluation, sharing, or preprocessing. So option B over here is not correct. It does not need 8 rounds of communication. So this is not correct. So now let's go to problem 5. So problem 5, it says that it has the same, the problem is kind of same. So in this problem, we have 3 parties, P1, P2, P3, and it uses the 3-party MSS protocol. And the dealer, P1 is the dealer, and P2 has the inputs X1 and X2, P3 has the input X3 and X4. So in the MSS protocol, this is a asymmetric, this is kind of an asymmetric protocol. So where we have a distributor, sorry, this is P2 and this is P3. We have a distributor over here, and P2 and P3 are the evaluators. And it says that P2 has the inputs X1 and X2, and P3 has the inputs X3 and X4. And together they want to compute the function this. So let's see how this is possible. So in the MSS protocol, so let's recall the MSS protocol briefly. So in the MSS protocol, we have this distributor and 2 evaluators, E1 and E2. Now the distributor only creates 2 OTP 2 random elements for OTP encryption, lambda1 and lambda2. And E1 and E2, they are supposed to hold MS lambda1, and E2 supposed to hold MS lambda2. What is MS? MS is basically, so if S is our secret, then MS is supposed to be S plus lambda1 plus lambda2. So in this way, D would require MS to compute this S. E1 would require lambda2 to compute this secret S, and E2 would require lambda1 to compute the secret. So this is exactly equals to what we have seen in this RSS sharing. So in MSS sharing, we just use a asymmetric way to compute this shares for D, E1 and E2. So anyway, so the task is easy for us because as we have seen, as we can see here, P1 is the dealer, or rather we can just call it a distributor. And P2 and P3, they have the inputs X1, X2 and X3, X4. Sorry, do you have a question?
Oh, sorry. I did not realize it was not on mute.
Okay.
Sorry.
Okay, so as I was saying, so we have participants P1, P2, P3. Now, if so, suppose that this is our dealer, not, or rather we can say that this is our distributor. And P2 has a secret S. So how do they? So how do they have the secrets? So our goal is that P2 would hold ms lambda 1 and P3 would hold ms lambda 2, and P1 would only have lambda 1, lambda 2. So this is our goal. So what happens is that P1 generates lambda 1, lambda 2 first. So that is the first step. And after that is done, whoever is the dealer. So here P2 is the dealer because P2 has the secret S. So P1 sends both lambda 1 and lambda 2 to P2, and only lambda 2 is shared with P3. So this stage, it requires only one round of communication with 3 ring elements. Now P2 computes ms as is plus lambda 1, lambda 2. Now that ms is communicated to P3 only. So the sharing, this takes again one round, and only one ring element is shared. So this was how the distribution, this is how the sharing works. So let's first check this first option. So first option said that during the preprocessing phase, the dealer P1 sends to the parties P2 and P3 14 ring elements each. Okay, so basically P1, P2, P3. P1 has X1 and X2, and P3 has X3 and X4. So since P1 is the one who has the X1, so corresponding to X1, so corresponding to each of these inputs, P1 generates 4 random lambda 1, lambda 2 pairs. And since P1 wants to generate, P2 has X1 and X2, so both lambda 1 and lambda 2 corresponding to X1 and X2, those are sent to P2. Lambda 1, and only lambda 1s are to be sent to P2 corresponding to X3 and X4. Similarly, only lambda 2 is supposed to be sent to P3 corresponding to x1 and x2, because x1 and x2 is with P2, and corresponding to x3 and x4, both lambda1 and lambda2 are to be set. x3 So in the preprocessing phase, we have total 6 elements that are to be sent to each of this P2 and P4, P2 and P3. But we also need to require some preprocessing data for multiplication. So now let's look at the multiplication briefly. So suppose in the multiplication phase, we have this P1, P2, P3. So P1 is the dealer over here, the distributor, and P2, P3 are the evaluators. So according to the protocol, so suppose we have corresponding to A and B, it holds lambda1, lambda2. And P would hold MA, lambda1A, MA, lambda2. Now, this somehow wants to generate a share for C is equals to AB, such that P1 would hold some lambda1, lambda2 corresponding to C, and over here it would hold now this MC is basically nothing but AB plus lambda1C plus lambda2C. Which is, so now we can write A as MA plus lambda1A oh sorry, not MA plus lambda1A, it should be MA minus lambda1 to lambda2. Plus this lambda1C plus lambda2C. Now that can be written as MA MB minus MA lambda1 lambda1B minus MB lambda1A plus lambda C1. Oh, sorry, lambda1C. This plus MA plus minus lambda 2B minus MB lambda 2B to A to C. This plus lambda 1 lambda 1A plus lambda 2A lambda 1B plus lambda 2. So you can check that this this term can be reduced to this. Now, one thing that we can verify is that this MA, MB, lambda 1B, lambda 1A, lambda 1C. So suppose that this lambda 1C is with So it's lambda 1c has to be with P2, and lambda 2c is supposed to be with P3. So then all these shares MA, lambda 1b, MB, lambda 1a, and lambda 1c, all these are with P2. So P2 can locally compute this value. Similarly, these values are available with P3. So P3 can locally compute these values. And since all these lambda values are with P1, so then P1 can locally compute these values. So now what P1 can do is that at the time of evaluation, P1 can just not at the time of evaluation, because at the time of pre-processing, P1 generates these values: lambda 1a, lambda 2, lambda 2a, lambda 1b, and lambda 2b. So at the time of pre-processing, P1 can actually generate, so let's call it as gamma c. So then P1 can just create the secret sharing for this gamma c and name it as gamma c1 and gamma c2. And this can be shared with P2 and P3 respectively. So now we can just forget about this, and we can say that there are shares gamma c1 and gamma c2 at the time of preprocessing that P1 has sent to both this P2 and P3, and the sum can now be is equals to MC. So MC now can be computed by both P2 and P3 in this way. So at the time of for this evaluation, this gamma 1, gamma 2, so P1, P2, P3. So P1 basically generates gamma C1, gamma C2, these two values, and it also, sorry, not gamma, is lambda, and it also computes this gamma, the secret shares for the value generated using these two values. So P1 would generate these values, and then it would send all the values to P2 and P3. So gamma 1c and gamma 2c, so lambda 2c and gamma 2c, that is supposed to be sent to P3, P2, P3. So if P1 can send these values to P2 and P3, then they can easily compute MC with them. So gamma 1, lambda 1, lambda 2 will be with P1. Lambda 2 is sent to P2, and lambda 1c is sent to P2, and lambda 2c is sent to P3 at the pre-processing space. And then when they have these values, P2 and P3 can locally compute these MC values. So they can now have this secret share for C, which is the multiplication of A and B. So this is how the multiplication circuit can be evaluated. And since we have only one multiplication in this circuit F, then along with this preprocessing data, there is also extra preprocessing data that has to be sent, which is lambda C1 and gamma C1. Similarly, over here, we need to send lambda 2C and gamma 2C. So there are total 1, 2, 3, 4, 5, 6, 7, 8. So 8 ring elements is supposed to be sent to each of P2 and P3. So therefore, this is true. 8 ring element has to be supposed to be sent to each of P2 and P3. Now, during the pre-processing phase, the dealer P1 sends P2 and P3 14 ring elements. This is not true. As we have seen that this is 8 is true. 8 is the correct answer. Okay. Now, not including the reconstruction phase, the total number of ring elements exchanged between P2 and P3 during this protocol are 6. Okay, let's check that. So if we do not include the pre-processing phase, so in the pre-processing phase, basically P1 sends some values to P2 and P3. So at the evaluation phase is where the communication is supposed to be. Okay. So at the evaluation stage, this C is equals to AB. So compute this C is equals to the shares for C is equals to AB. The P2 and P3, they did not have to communicate communicate, because P2 and P3 already had all these shares MA, MB, lambda 1B, all these shares. So therefore, they don't have to communicate for evaluation, but they have to communicate for sharing. So at the sharing stage, as you can see, that if P2 has the share S, then P2 has to communicate one ring element to P3. So therefore, okay. Okay, sorry, I made a mistake. This is one share for MC, and this is another share for MC. So after this is done, P2 can communicate this one share for MC, and P3 can communicate one share for MC, and then they have to communicate this computed values, and then only they can compute back the MC. P2 and P3 both can have the MC then. So there is one other communication for evaluation. So for evaluation, they must communicate two ring elements. And for sharing, they must communicate one ring element each. So if all the pre-processing data are shared among them, then for x1, x2, and x3, x4 are the inputs. And for x1, P2 has to communicate one ring element. For x2, P2 has to communicate one ring element. Similarly, for P3 would communicate two ring elements for x2 and x3. And for evaluation, there is one multiplication circuit. So therefore, P2 and P3, they would have two ring elements communicated among them. So there are total 6 ring elements that are to be communicated in total. So C is also true. Now, if C is true, then obviously D is not true, because the total ring element that we have already calculated is 6, not 12. So these were all the problems that we had for week 6. Now, to solve some problems for week 7, let's recall all the problems that we have for week 7. So first of all, let's talk about this 1 out of 2 OT scheme to 1 out of n OT scheme. So what was the OT scheme for 1 out of 2? So OT scheme was something like this. So suppose that we have a OT scheme, the oblivious transfer protocol. So in this transfer protocol, one side we have Alice and the other side we have Bob. So Alice have two inputs, M0 and M1. These are all secret inputs. And similarly, Bob has one input B. And using the oblivious transfer protocol, they can somehow manage to Bob can manage to get the message MB. Now the condition is that Bob can only get MB, but Bob cannot get MB1 minus B. Cannot get any information about 1 minus B, M1 minus B. So basically, Bob can read either one of this message, that is M0 or M1, not both. And similarly, Alice don't have any information about B. That means which message that Bob is reading, Alice don't have the information about that. So this was the oblivious transfer. Now using this 1 out of 2 oblivious transfer, we have to create a 1 out of n oblivious transfer. Now for simplicity, first we just consider n is equals to some 2 to the k. That means n is of this form. Then we can write any number. So basically 1 out of n in oblivious transfer supposed to be something like this. So if this is root t, so then Alice would have n many messages, m0, m1, to mn minus 1. So m many messages on this side Alice would have, and Bob would have one I, where I is, so basically we can just say that I is in Zn. And Bob can only get back what mi is. The information about any other messages, that will not be revealed to Bob. So this is what we want to achieve. Now using the 1 out of 2 oblivious transfer protocol, we are going to construct this 1 out of n oblivious transfer. So basically what we can say is that for any I belongs to Zn, since n is 2 to the k, where k is log n, log 2n. Since n is equals to 2 to the k, then we can say that any I can be written as k-bit binary number. So let's say that this I is nothing but b0, b1 to bk. Now what we can do is that Alice have these messages m0, m1 up to mn minus 1, and Bob have this binary array. Bob has this I, which can be written as b0, b1 up to bk. Now what Alice would do is that it can generate, Alice would first generate k0, k1. Okay, 0. Okay, not 0. So basically Alice would generate k many pairs of keys. Okay, there are 2 keys. Okay, so let's call it t instead of k. So it should be bt. So Alice first generate t many pairs of this case, k0t, k1t. So this is what Alice would generate. Now Alice would now use this oblivious transfer for each of this ki. K0, K1, not Ki. It should be like it's a Kj. What is J from 1 to T? So this is a 1 out of 2 OT. So this is a 1 out of 2 OT. And over here, Bob inputs Bj. So Bob has this T many inputs, B0 to Bt. So using this 1 out of 2 OT, Bob can now get only KBJ, right? So Bob can only get this value. So Bob can only achieve one of these keys, either K0 or K1. So using this protocol, Bob can get K many keys from this. Okay. Let me save this. Okay. Now Alice uses the encryption CI is equals to, so if I is can be written as this P0, P1 up to Pt, then CI would be something like this. CI would be what's that? Wait a minute. All right. So CI can be written as KB0 J. Sorry. Some encryption of, not encryption, we can use some one-way function f of I with the key as k p0, that's what with f of I kp1 f of kpt I SOR the message mi. Right. 1 2 t. Right. So this is the way we do the encryption. So if I is indeed the input for I was the input for this 1 out of n in this 1 out of n OT. If I was the input and if I is this B0 to BT, then the encryption CI would be something like this, and Bob would get this KB01, KB02, and KBTT 1, 2. Okay, so this is not B0 to BT, this is B1 to BT, B1, B2 up to BT. So there's a problem with indexing. Right. Right. So Bob can Bob will get all these values. So if Bob can get all these values, then Bob can easily decrypt this. Bob can easily get back this CI. But for any other For any other I that is not equals to this, not equals to I, so let's consider that is I dash. So, and I dash is I dash not equals to I, such that I dash is equals to B0 dash, B1 dash, not B0, B1 dash, B2 dash, up to BT dash. Then there will be some Bj such that Bj is not equals to, there will be some J such that Bj is not equal to Bj dash, since I is not equals to I dash. And for that particular Bj dash, Bob cannot compute this value. B I dash A Bj dash J dash. Sorry, not J dash, it's J. So Bob cannot compute this value, and if Bob cannot compute this value, then Bob cannot really have this, cannot really reconstruct this message MI. So therefore, Alice, Alice and Bob can convert this one out of two OT protocol to one out of n OT protocol. Now over here, as you can see, the number of pairs that Alice generated is log n. Only log n many pairs has to be generated by Alice. Also, to generate all the ciphertext, Alice has to, for generating each of the ciphertext, Alice has to evaluate this f. Invoke this f. How many times? Log n many times. So for all of this, to generate all of the ciphertext, that would be n log. And then all of this n ciphertext has to be sent to Bob. And at the Bob side, it will only take log n invocations of f to get back the MI. Okay, so now next look at how RSA scheme works. So in RSA, what we have here is that first we generate two prime numbers P and Q, and we set n is equals to PQ. And we also compute the phi n. Phi n is basically the number of elements that is co-prime to the number of elements in Zn. So phi n is basically the number of elements in the set, and the set is all those elements x in Zn such that GCD of x and n is 1. That is all those elements that are co-prime to n. So this is our number phi n. Now if p and q are prime numbers, then phi n can be calculated as this: p1, p minus 1, q minus 1. So this is our phi n. So phi n is p minus 1, q minus 1. Now to generate the RSA parameters, so first we have to sample an element from Z phi n such that GCD of E and phi n is 1. So this is step 1. Step 2 is that since GCD of E and phi n is 1, then we can efficiently compute a D such that ED will be concurrent to 1 mod phi n. And there are two parameters in RSA: public parameters and private parameters. So private parameters are not supposed to be made public, and public parameters are the ones that are made public. So public parameters are in E, and private parameters are only P, Q, T, and phi n. So these are not supposed to be made public. Okay, so now how the schemes work? So the encryption scheme. So the encryption scheme works in this way. So we take any message M from Zn star. So since we have E as the public parameter, the encryption works in this way: M to the E mod n. Similarly, the decryption works in this way. Sorry, so it's supposed to be M dash is equals to C to the D mod n. Now, if C is computed like M to the E, then and M dash is computed like C to the D, then M should be equals to M dash. This is how the RSA encryption and decryption works. Now, from Zn star to Zn star, the function, consider the function f of M as M to the E mod n. This is the RSA one-way function. RSA function. So if this is our f, then this function is a one-way function. That is, for any function, for any input M, we can compute f of M. But given f of M, computing this M back is a hard problem, computationally hard problem. Or rather, we can just say that any PPT adversary have negligible probability to compute M. So this was what the RSA problem was. Now let's talk about the RSA based OT, the oblivious transfer, the RSA based bit OT. So as we have seen in the RSA problem was like this. So we have this X and this one, sorry, this one, Zn star. Zn star, we have the function f. The function f works in this way into the E mod n. So if this is our function, then this is a one-way function. Now let's consider. So as we have discussed about this definition of this hard predicate, so let's consider this hx as LSP of the least significant bit of x. That is to decide whether this x is an even number or odd number. So if this is our function f and this is fx, then now the problem is to find hx. That means we have been given this fx. This is a public. Now the challenge is to find hx given fx. That means the challenge is to find whether this x is a even number or odd number if we are given this fx. So that is a hard problem. I mean, that is proven this is a hard problem, and such functions are called hard predicates. Sorry, not hard predicates, so it's hard code predicates. So RSA is basically, so this is a hard code predicate, this LSB of X. Now using this, we can create a bit OT for RSA. So over here, using RSA, we have Alice and Bob. So in this bit OT, Alice has two messages, M0 and M1, both belongs to the 0, 1. And Bob has this bit MP. Now, so how do they compute this? How do they use this RSA-based OT? So we have the public parameters for RSA, which is N, E, and the private parameter for RSA was, so public parameters is known to Bob, which are N, E, and private parameters are P, Q, Phi, and D. This is only known to Alice. Alice is the one that creates this parameter. Now, what Bob does is that Bob first sample SNT in Zn star. And then computes S like this. Now what Bob would do is that Bob would either send S and T as the message, or T and S. If B is equals to 0, then Bob would send this, and if B is equals to 1, then Bob would send first it would send T, and then it would send S. C0 and C1. And after this is sent, what Alice can do is that Alice can find out the values. Okay. Now what Alice would do is that Alice would find out R0 and R1 as the LSB of C0 to DT model, LSB of C1 to DT model, and Alice would now send R0, sorry, M0, and R1, sorry, M1 to Bob. Now Bob can generate the message M0 and M1 by, okay, so if this is D0, let's call it D0, and this is called it D1. Bob can generate M0 and M1 by computing D0s or R0, and D1 is or R1. Now, the thing is that if Bob had the value, I mean, initially Bob chosen B is equals to 0, then S is sent as C0. And whatever Alice has computed over here, Bob can compute this value, D0, R0, because this LSB, this R0, which is the LSB of C0 to T mod N, which is nothing but LSB of S to the D mod N. Now S to the D mod N is nothing but S mod N. Now S was the value that was chosen by Bob, so Bob can easily compute this value R0 and compute this M0. But can Bob compute this compute the value R1, which is LSB of C1 to the T? Now C1 was T, and T was randomly chosen by Bob. So Bob cannot really compute this value R1, since Bob doesn't know the value T. So this is not possible to find out for Bob. But on the other hand, if B was 1, then C1 was, the Bob sends Alice the value C value is as C1. Then Bob can find out the value R1 but not R0. So then Bob could get the value, get the message M1 but not M0. And one very important thing to remember is that the assumption is that these are, uh, I mean, we are considering non no malicious. Sorry, we're considering the adversaries are not malicious. So if Bob was malicious over here, then Bob could just compute Bob could just sample S and T from Z and star, and then compute corresponding S and T, which is nothing but S to the E and T to the E. And if Bob would do that, then Bob can Bob can get back both message M0 and M1. So therefore, this protocol would not work in this case. In that case, so the assumption is that the Bob Bob is not a malicious adversary. Okay, so this is the end of this today's live session. Let's meet in next week again. Thank you.